Pressure, volume, temperature. You've seen or felt all of these variables, but did you know how they relate to one another? In an ideal gas, a few factors explain how it will react. Have you ever noticed how your car tire pressure decreases in the winter? You've seen gas laws in action. Pressure, volume, and temperature are all related in an ideal gas, or a gas that has perfectly elastic collisions, random motion, and obeys Newton's laws of motion. While no gas is perfectly ideal, we assume they are for the sake of solving for a relationship. Boyle's law shows the relationship between pressure and volume at a fixed temperature. Pressure and volume have an inverse relationship, meaning as pressure increases, volume decreases, so P1 V1 equals P2 V2, where P1 is the pressure and V1 is the volume, and P2 and V2 are the pressure and volume afterwards. So let's work through an example. So for Boyle's law, P1 V1 equals P2 V2. So if the volume in a cylinder with a movable piston decreases from 10 meters cubed to 6 meters cubed, and the original pressure is 30,000 PA, what is the final pressure? So our given information, we have the volume initial, that's going to be 10 meters cubed, and we have the volume final, and that's going to equal 6 meters cubed. And then we have the original pressure, which is the initial pressure, so the P1 is going to be 30,000. So all we have to do is plug it into the equation. So we have 30,000 times 10 meters cubed, that's the original volume, equals P2, which is what we're solving for, multiplied by the final volume, which is 6 meters cubed. And if you work through that calculation, 30,000 times 10 divided by 6, you're going to get 50,000 PA. So our final pressure is going to equal 50,000 PA. Charles' law shows the relationship between temperature and volume at a constant pressure. Volume and temperature have a direct relationship, meaning as volume increases, temperature increases, or vice versa. Molecules move faster when you add more heat, meaning there are more frequent collisions with the sides of the container. At constant pressure, volume will increase. So V1 over T1, which is the volume initial over the temperature initial, equals V2 over T2, which is the volume final over the temperature volume. And also, temperature has to be in Kelvin, or else the calculation won't work. So let's work through an example. For Charles' law, we have the volume initial divided by the temperature initial is going to equal the volume final divided by the temperature final. So the temperature in a cylinder with a movable piston is increased from 174 Kelvin to 298 Kelvin. If the original volume is 300 meters cubed, what is the final volume? So what we know is the T1, which is 174 Kelvin, and then we have the T2, which is going to be 298 Kelvin. And we have the original volume, which is the V1, and that's going to be 300 meters cubed. So let's just plug it into the equation. V1, which is 300, divided by T1, which is 174, equals the V2, which is what we're solving for, divided by the T2, which is 298. And with that calculation, 300 divided by 174 multiplied by 298, we're going to get 513.8, and that's going to be in meters cubed. So that is our final volume. Gay-Lussac's law shows the relationship between pressure and temperature at a constant volume. Similar to Charles' law, as you add heat, there are more frequent collisions from the molecules to the sides of the container, increasing the pressure with the equation P1 over T1, which is the initial pressure divided by the initial temperature, equals P2 over T2, which is the final pressure divided by the final temperature. So let's work through an example. So for Gay-Lussac's law, we have the pressure 1 divided by the temperature 1 equals the pressure 2 divided by the temperature 2. So in a fixed volume container, which means that the volume is going to stay constant, which allows us to do pressure and temperature, the pressure is increased from 30 kPa to 100 kPa. Now, even though the standard units for pressure is PA, because we have two of them and they're both in kPa, we can keep them in kPa because the units will cancel. So if the original temperature is 30 degrees Celsius, what is the final temperature? So you may remember the standard units for gas laws are Kelvin. So to make our 30 degrees Celsius into Kelvin, what we're going to do is we're going to add 273 to that. So we have 30 plus 273, which is going to equal 303 degrees Kelvin. So now we have all the information we need to solve. So we have our 30 kPa, which is our pressure 1, the initial pressure. P1 is 30. And our temperature 1, which is the original temperature, is going to be 303 K. Temperature 1. And we have our final pressure, which is going to be 100 kPa. So our P2 equals 100. So now we're just going to plug everything in and solve. So we have 30 divided by 303 equals the pressure 2, 100 divided by T2, which is what we're solving for. So now we solve. So we have 30 divided by 303, and then we have 100 divided by that answer. So what we're going to get is that the T2 is going to equal 1010 Kelvin. The ideal gas law shows the relationship between temperature, volume, and pressure. This law combines all of the previous laws into one. So we have P1 V1 over T1 equals P2 V2 over T2. Therefore, PV over T is a constant if the number of molecules is constant. So we have PV over T equals a constant, which will be the number of molecules, N, times the constant R. R is the universal gas constant, and in physics, this value will most likely be 8.31, and the units are going to be joules per mole Kelvin. And if it's not, the number will be provided. So to solve this out further, we multiply by temperature over here, so we have PV equals nRT, where P, the pressure, is in pascals, volume is in meters cubed, and N is the number of moles, and temperature is in kelvins. If the units are not standard units, you have to change them, or else the calculations will not work. Also, in physics, sometimes the ideal gas law, PV equals nRT, will be written as PV equals nKBT, where N is the number of molecules as opposed to the number of moles, and Kb is the Boltzmann constant, which is going to be 1.38 times 10 to the negative 23rd joule per Kelvin. So let's work through an example. So for the ideal gas law, we have PV equals nRT, the pressure times the volume equals the number of moles, the gas constant, and the temperature. We also have PV equals nKBT. That one's the pressure times the volume equals the number of molecules times the Boltzmann constant times the temperature. So for this example, 3 moles of hydrogen gas are in a fixed volume container of 0.53 meters cubed where the temperature is 130 degrees Celsius. What is the pressure in the container? So you may ask yourself, which equation will I use? Well, in this problem, we have 3 moles. So that means we're going to use the one with the little n and the r, because this is number of moles and this one's number of molecules. So we have PV equals nRT. R is going to be 8.31 joules per mole Kelvin. So we're solving for pressure. Our volume is going to be 0.53 meters cubed. Pressure times 0.53 equals the number of moles, which is 3, times R, which is 8.31, times the temperature. Now our temperature is given in Celsius, and that needs to be in Kelvin. So we're going to do 130, that's the Celsius, plus 273, and that's going to equal 403. So our temperature in Kelvin is going to be 403. And now we just solve for the pressure. So we're going to do 3 times 8.31 times 403 divided by 0.53. And our pressure is going to be 18,956 pascals.
In this demonstration, I'm going to show you Boyle's law. The materials you will need are a small balloon and a large syringe. So first, you're going to start out with the plunger pulled as far as you can, and you're going to put your finger on the open end to create a closed system, and you're going to push the plunger in, and as you can see, the balloon is decreasing in volume, and this is because you're pushing the plunger in and the volume is decreasing of the syringe and the pressure within is increasing. Therefore, the air molecules of the balloon are now closer together. For the second example, start with the plunger as far as you can and put your finger on the open end to create the closed system and pull the plunger out. As you can see, the balloon is increasing in volume. This is because as you pull the plunger out, the volume of the syringe is increasing and the pressure within is decreasing. Therefore, the air molecules are farther apart within the balloon.